Oh, thank you very much.
Sorry.
It's got to be bonded to something. And I'm missing you because we're talking about things making molecules being bonded. When you're just talking about N, not follow. N does not behave by itself. If you have just an N, it's going to be reacting violently to try to find something to bond with and share its electrons with. So N we don't even talk about by itself. Are you trying to put N by itself?
Yeah.
No.
No, those are all.
Yeah, when it's bonding to
There's no
something,
deltas.
is when it's full.
Just type in
Because it's got to be taking the electrons away from something else, like that tug of war. You can't play tug of war by yourself, right? Anytime you have a diatomic, you have two things that have the same electronegativity trying to pull the electrons away. They can't, but the electrons will be shared right in between the two. That's why I had the halogens up here. They're all diatomic, so they're totally non-polar. Like an F2. F is very electronegative, but when it's trying to pull electrons for another F, the two Fs don't, one doesn't win over the other one. So any diatomic is going to be non-polar, even if it's FON or CL. Varun? Talk loud so the camera can hear you. That was no louder. What's the nucleus made of?
No. What? If
Wait.
it pulls in electrons, it's going to be positive.
You can probably just turn the camera now. Thanks, buddy.
What are you missing there, bro? Are you mixing up the electron cloud with the nucleus?
Yeah.
Don't
Or
say
the
that,
bond?
Varun.
No, except the electron clouds.
Okay. Okay. All right. Here's an example of hydrogen bonding. Go ahead.
Tons of fun.
Yeah. But this is not in water. This is just pure HF. And so it's not acting as an acid. For something to be an acid, it's got to be in water so the water can take its hydrogen. Okay? All right. So just HF, pure. This would be a gas. And you have an H that's attached to it. Now, when I show you the bond between the H and the F like this, it doesn't really give any indication of where the electrons are that are being shared. But when I show an overlap of the orbitals, and I draw like a cloud, in this case a red cloud, that shows the density of where we expect the electrons to be, notice the electrons are much closer to the F, because it's more electronegative. And so the electrons are drawn that way. What winds up being over here? Remember what hydrogen is. Simplest element, what's hydrogen made of?
One proton.
How simple can you get? One proton with one electron. And what's happening to its electron? It's getting pulled away from it. So what winds up over here?
Just a proton.
Just a proton. And so this side of the molecule is just this wide open exposed proton, positive, very positive proton, that's not protected by anything. There's no inner electrons to kind of shield it or cover it. So you've got a very, here's a different color, a very positive region over here on this side of the molecule. And over here we have, this is yanking the electrons. This is very negative. Not only is it negative, but notice the fluorine is covered with lone pairs of electrons. Yes, exactly. So the next HF molecule is going to have this negative side to it. I'm sorry, this positive side over here. So how do you think these lone pairs feel about this exposed proton?
They love it.
They're very attracted to it. So that draws those particles. I mean, remember, this is a wide open proton. It's just open, it's positive region. So all these lone pairs are kind of digging that proton. They just pull themselves right over there. Yeah.
So it doesn't have to be just an HF, just an HF. Between HF and HCl.
Yes, it could. That's right. That's why polar things tend to mix well together, is because of the separation of charges. Yep. Now, I need you to know that water is a very special case. Yeah, these all have hydrogen bonding, and that's fine. You got an H attached to FO and a Cl. But water is unique. Water has some very special properties. Why? Because it's got two hydrogens And every molecule's got 2 lone pairs. So theoretically, every water molecule could make 2 hydrogen bonds. This is showing 1 hydrogen bond. This would be one of the lone pairs on that oxygen with a neighboring hydrogen. And then the other lone pair, which would be over around in here, that could be attached to another water molecule's hydrogen. And so water winds up having a very high boiling point because the particles are so attracted to each other. Water has a very high specific heat because it's tough to get water to move faster, where the water molecules three-dimensionally are so attracted to one another. Want to try to get it to wiggle around faster, it takes a lot of energy. It's got a very low vapor pressure because the particles don't want to evaporate. So water is kind of the king of intermolecular attractions because it's got the 2 sites for hydrogen bonds. More so than even something like this. This is a very polar bond. The water wins because it's got the 2 parts for the hydrogen bond. Okay. Now, before we move on to the last topic, we've got a couple of minutes. I want to show you, this topic, by the way, is in Chapter 10. This is the one thing that's in Chapter 10. Hybridization was in Chapter 9. That's all that's in Chapter 9 that we have to do. And then the intermolecular attractions are in 10. This is questions out of the end of Chapter 10. There's 41 and 42, and I think there was some other questions that we had. But I'm going to tell you, I want you to listen carefully. On the quiz tomorrow, there will be parts of 41 and 42 on your quiz. I'm telling you that there are going to be. Before other questions, but guaranteed 41 and or 42 are going to be there.
Wait, the same,
Well, guaranteed 20.
like even though you're not
No,
gonna
wait.
change the
With both of them?
problem.
Just one.
Oh, I might change what the substances are.
Oh wait, well it's not that bad. Yeah.
What are there? A through F here, and I think 42 has A through F. There's like 12. But A,
With London dispersion forces, isn't there something about surface area also that matters?
well, I don't know how much surface area matters because the bigger the molecule gets, the more surface area it's going to have.
But then there were.
So I think that it goes with the molar mass.
I
Then
don't,
what?
I don't remember where I saw this, but there was one where it's like the same molecular formula, except one of them was like all bent up and like into a ball, and then the
I
other
see what you're
wasn't.
saying. Yes, 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 yes. When you have branched chains, now we're going back to organic. When you got a lot of functional groups, those molecules don't fit together as well as when you just have an unbranched chain. Could you see that happening? Like if we had a long chain, let's just like a polymer, polyethylene or whatever. If you've got a bunch of those chains like that, they fit together very nicely. And so that would be a strong polymer because of the particles, the molecules do have tons of dispersion forces going on. If you have functional groups, like maybe benzene rings or even chlorines or whatever, how well do they fit together? Like spiky, isn't it? And so they don't fit together as well. So that's more than you need right now. But yeah, I think that's important to recognize that in organic molecules, the straighter the molecules are, they tend to have the best fit with one another, and they'll boil at the highest temperature because they're stuck together. The more branches molecules have, more functional groups, the less they stick together. Thanks for mentioning that too. I think that's good. I'm glad you brought that up.
That can be seen like the linear molecules or whatever.
Yes.
Yep. So there'd be a higher boiling point than like say a trigonal pyramidal.
Then a what?
Than like a pyramidal.
Really, that topic is for the big molecules. Like a pyramid, you got one central atom and some things around it. I'm talking about chains of molecules that have functional groups on it. More so than that happens. Okay. Let's take a look at A, B, and C to see if we can get anything out of this. When you do these questions, I want you in your mind to be thinking about what the particles are doing. Make a particle model in your mind. If we're talking about boiling point, what do you picture the particles doing?
Boiling.
What do they look like at the beginning of the process?
Oh, like stuck together.
They're all stuck together as liquid. And then the particles have to be broken apart. Is that an exothermic or endothermic process?
Endothermic.
It's endothermic. Energy must be put into it, so the particles are wiggling around faster and faster. Eventually, they break apart. Which of these three would it take the most energy to get them to break apart and go into the gas phase?
HBr.
So we have the three choices.
Okay.
Are any of these polar molecules? Or is there any hydrogen bonding?
Yeah.
Yeah.
What?
No, really? Of course.
Is there any hydrogen bonding in any of these?
Absolutely.
Yes.
Oh. It's not
Yes.
I don't feel so good.
Oh.
Have I not taught you anything?
No, but you're asking for hydrogen bonding specifically.
No, he's talking
Oh
about.
my God.
I thought that's what I said.
Nah.
All right, so anyway, maybe I'll just answer my own question.
Yes, please.
These are all non-polar because there's no FON or CL. There's CLs, but they're attached to one another, and so then that's a non-polar thing. And so there's no hydrogen bonding because there's no H's attached to FON or CL. So whatever you said in response to my question, why were you saying there was hydrogen bonding? Because you saw hydrogen. Yeah, it's got to be an H on an FON or CL. So seriously, thank you for making that mistake, because if anybody else was thinking that, you must have the H directly attached to FON or CL to have hydrogen. Not enough to have a hydrogen in a bond. And it's not even enough to have a hydrogen in the same molecule as FON or CL. It's got to be attached to it. No, there's no hydrogen bonding in this.
It has to be.
Okay. So it seems like if none of these are polar and none of these have hydrogen bonding, then the London dispersion forces are going to be the one that dictates the winner. This has a molar mass of 82. 81, I'm sorry. Bromine is 79.9. It's close to 80 and then plus 1, 81. Krypton is 83.8. Krypton's a little bit heavy. And then Cl2 is 71. So the krypton is a bit heavier, but time out.
Yeah.
They're all pretty close. Would you agree that they're all pretty close to one another? 71 to 83. What would you say about HBr?
It's a
I'm going to
di-
contend that HBr is the winner here. It's going to be the most attracted to other molecules that are HBr. Why?
Because it's a dipole.
It's a little bit polar. It's certainly, this is totally non-polar. This is not even a compound. It's just atoms of krypton. But this is H and Br, and Br is a halogen, so it's kind of far to the right. Even though it's not one of the principal dipole elements, I'm going to contend that this, being about the same size as krypton, is going to be a little bit more attracted to other HBr molecules than krypton. Krypton's a noble gas.
Right.
Those particles are not attracted to each other.
So then you
still has boiling point.
Now you're going back to what you saying it's polar.
I'm saying it's a little bit polar.
It's still not.
Shree? That's kind of tricky, I know. If it would have said HCl, it would have been way more obvious. You should say, oh, that one's polar, it's good. It's going to be the highest boiling.
So now we look at the molar. Who has the highest molar?
Highest what? Molar mass. Yeah, but there's not one clear one. I mean, krypton is the highest molar mass, but it's just a little tiny bit, a couple grams per mole higher than that. So because that one is a little bit polar, separation of electronegativity, then that one wins. I know it's tricky. Now the next one's hard too. Some of these are hard questions. That's why I want to go over them with you. B, the highest freezing point. Now what's happening in freezing? What are the particles doing? They're a liquid, which means they have freedom to move, and then they crystallize. Which one of these would have the highest freezing point? Which one would crystallize at the highest temperature? Now we're used to thinking about liquid water because we're used to liquid water. We don't know anything about HF. I did say that, but before that we didn't know anything. And then NaCl, we're not used to liquid sodium chloride. So let me just turn the question around a little bit. This is asking about freezing point. Freezing point is the temperature at which a liquid changes to a solid. Would that not be the same as the substance's melting point?
Makes sense.
Freezing point is the same temperature as melting point. It just depends on what physical state you're going to what. If I was, let's use water. If I was freezing water, I'd start with liquid water, and I've got to cool it down to what temperature? 0. 32 Fahrenheit, 0 Celsius, then it freezes. Okay, now I have ice at -15. What temperature do I have to raise that ice to get it to melt?